Hello my dear students. So I am going to start a new topic, extraction of iron. But we have discussed this in relation to the activity series. So you all know the order of metals in the activity series. What is it? We start with potassium, sodium, calcium, magnesium, aluminium, then we have zinc, iron, tin, then lead, hydrogen, then we have copper, mercury, silver, platinum and gold. So in that, when we discuss the uses of activity series in the previous chapter, you all can remember students, by looking at the order, we can identify the metals that are highly reactive, then the metals that are moderately reactive, and also the metals that have very low reactivity, or what we call as the native metals that exist as metals in nature itself. So based on their reactivity, the method of extraction also changes. So if you take the highly reactive metals like sodium, potassium, we extract them using electrolysis of their salts. For example, sodium chloride is obtained from the seawater, the salter. Then the sodium chloride, if we take it in the fused state, we can electrolyze that and extract sodium metal. Same goes for potassium as well. Then we saw that the moderately reactive metals like iron, zinc, copper, lead, all these metals can be extracted by reacting with another element or a compound. So as an example, I told you all, iron is extracted using carbon monoxide. Then the last few metals like platinum, gold, silver, these are the silver, platinum and gold, the last three elements in the activity series, the last three metals that are very less reactive. So they exist in the form of metals itself. That is why we call them as native metals. And they need to be separated from their impurities only. So for that we use very simple physical separation methods. So in this chapter, I'll be discussing two methods. One is the extraction of iron. So that is a metal that has moderate reactivity. And the extraction of gold. That is a metal that has the lowest reactivity, the last metal in the activity series. So with that introduction, students, we will look at the extraction of iron. Now let us pay attention to the extraction of iron, a metal which is very important for the life of the human. So why do we say very important for the life of the human? Now in our day-to-day life, we use so many things made up of iron. If you take the grills for windows, sometimes as protection for the doors, we have a grill that is usually made up of iron or steel. So steel is an alloy of iron. Then we have the utensils in the kitchen. Knife, spoon, fork, even the dishes that we use, vessels that are used for cooking, they are made up of steel, stainless steel. So like that, even in the laboratory, so many things that we use, the laboratory equipments, even the tripod, pair of tongs, then we have the test tube holders. So most of them use iron as the metal. So that is why it has been used from the ancient days. Even if we look at the history of our country, they have been able to extract iron and they have used that to produce so many things. Even things like swords and all those have been made using the iron extracted in our country. So that is given in extra knowledge. So for extra knowledge, you can see there are evidences in support of the fact that there had been a wealth of knowledge about extraction of iron in Sri Lanka in the past. So they have known how to extract iron in the past itself. So archaeological excavations carried out recently in the Samanala Weber area have disclosed that a furnace smelting iron ores had been operated with the aid of monsoonal winds. So what we will be discussing is also a furnace. It is called the blast furnace that is fueled or the temperature is provided by burning substances. But here they have used furnace for smelting iron ores. Smelting is liquefying and separating out the iron. So for that process, they have used monsoonal winds. To operate that, they have used monsoonal winds. And a group of archaeologists succeeded in reconstructing such a furnace and producing iron by smelting. So they have produced iron by smelting the iron ore. Then archaeological records state that steel for making the ceremonial sword of Emperor of Arab had been brought in from Serendip. So you all know our country was called Serendip. So there the ceremonial sword for the Emperor of Arab was made in our country. So we have an ancient history where we had the knowledge of extracting iron, and also we have carried out that process. So you should be actually happy and proud that we were able to do that even in the ancient days. So that the information or the evidence was found near Samanala River. That is for your extra knowledge, students. So with that understanding, I will move on to the next slide. So to understand the process of extraction of iron, first we will recall the activity series, students. You all can remember the order. I told you all have to know the activity series. So what are the elements that are highly reactive? It starts with potassium, then sodium, calcium, magnesium, aluminium, zinc, then we have iron, tin, lead, and thereafter for the purpose of comparison we use hydrogen, and after hydrogen we have copper, mercury, silver, platinum and gold. So that is the order of metals in the activity series. Potassium, sodium, calcium, magnesium, aluminium, zinc, iron, tin, lead, hydrogen, copper, mercury, silver, platinum, gold. Now you all can remember, students, we have discussed this before, the metals that are highly reactive, which are at the top of the series. Potassium, sodium, calcium, they are extracted by the process of electrolysis. Whereas metals that are native metals, they exist as metals in nature like silver, platinum and gold. We usually extract them. We actually need to separate them from the impurities present in their ores because they are present as metals itself. But the metals that are in the middle, zinc, iron, tin, lead, those are metals that have moderate reactivity. So here you can remember, students, these metals, these have moderate reactivity. Moderate reactivity. And out of those, we will be considering iron. Iron is a metal that has moderate reactivity. So it exists as compounds in nature, and you all normally know these metals are extracted from their naturally existing ore by an element or a compound, by reducing the metal from its ore using an element or a compound. So that is the process that we are going to discuss now. So here you can see iron is a metal placed somewhere in the middle of activity series. So here you can see middle of activity series. That is what I just explained to you. Iron is extracted from the iron ore. Iron ore mined from the soil. So you have to remember or understand the term ore. What is an ore? It is a naturally existing solid that exists in nature, so in the soil, which contains a metal or a mineral of its metal. So iron is present as compounds. For example, if we take Fe2O3. Now that particular compound of iron is called hematite, and hematite is the ore that contains iron. So in nature, iron is present in the form of hematite. So if we write that, here you can see the main component containing iron in the ore is hematite. And this has the chemical formula Fe2O3. You have to remember these, students. Hematite is the iron ore that is commonly used to extract iron, and that has the chemical formula or the molecular formula Fe2O3. So then, we use this hematite to extract iron, and now this ore is taken from the soil, and there it is not only hematite, there are other impurities also present. So the ore has to be separated, the iron containing compound has to be separated from impurities, and also iron has to be extracted. Now to do this, we use a particular structure that is known as the blast furnace. Now there are different type of furnaces. Now we discussed about smelting of iron. They are at high temperature, the extraction of iron. That is what we discussed in the previous slide. The same way, we use a furnace here which is known as the blast furnace, and here the temperature of blast furnace is provided by the hot air blast that is passed into the furnace. So a structure used to extract iron is called the blast furnace. Blast furnace. So you all have to remember that as well. Now it is a special furnace about 60 meter high. So 60 meter high means it's a very tall structure, and also it has a particular shape. It has inlets through which you send the hot air, and also from the top we add the or introduce the raw materials. There are actually 3 raw materials. One is the iron ore that we discussed, hematite, and to extract iron, we need to use an element or a compound. Here we use a compound that is carbon monoxide. Now this carbon monoxide, as you all know, is a gas. So we normally don't send the gas in the form of carbon monoxide. Instead what they do is they use carbon coke. Now coke is a type of carbon that can burn easily. It undergoes combustion very quickly, and also it releases lot of heat energy. So that advantage is there when they use carbon coke. So there is hematite, the iron ore, then there is carbon coke that is used to get carbon monoxide. That is the compound that is going to reduce iron from its ore. So thereafter, I told you all, there are some impurities in this particular hematite. So we need to remove those impurities. For that purpose, we use limestone. So that means there are 3 raw materials that are introduced to the blast furnace from the top of the furnace. Hematite, carbon in the form of coke, and limestone. Limestone is calcium carbonate. I am sure you all can remember that formula. So 3 raw materials. And it is a special furnace about 60 meter high, and the raw materials are fed into the furnace from the top, while hot air is blown in from the bottom. And this is called the hot air blast. So can you all understand that? There is hot air flowing from the bottom and the raw materials are introduced from the top because of the high temperature. Usually there is a temperature range between 1000 degrees and 1900 degrees Celsius. Very high temperature. And within this temperature range, there are many reactions taking place. And due to those reactions, iron is separated in the form of liquid iron or molten iron. Iron comes out as liquid iron or molten iron. So heating caused by hot air. Now I told you all this. Heating caused by hot air brings about several reactions inside the furnace, giving liquid iron. It's very important. Although we use iron in the form of a solid, a metal. But when we extract it, we get it as a liquid iron, or we can call it as molten iron. Both refer to the same thing, iron metal in the liquid state. So, heating caused by hot air brings about several reactions inside the furnace, giving liquid iron or molten iron. And the temperature range within the blast furnace, is 1000 degrees Celsius to 1900 degrees Celsius. And this is caused by one thing, the hot air blast that is introduced from the bottom. And as I told you, now coke is a form of carbon that can release lot of energy, high amount of heat energy when it undergoes combustion. So due to that also, the temperature is between 1000 degrees Celsius and 1900 degrees Celsius. So into this blast furnace, we introduce or we feed raw materials. I told you all the three raw materials. What are they? Hematite, that is Fe2O3. Then there is coke, that is carbon. And there is limestone, that is calcium carbonate. So the raw materials used are, if we write down the raw materials, they are hematite, that is Fe2O3. This is the iron ore. Then we have coke. Coke is carbon. And also we use limestone. Limestone is calcium carbonate. So you have to remember the reasons why we add these into the blast furnace. Now hematite is the ore that contains iron. So there we use it to extract iron. Then there is coke, carbon, that is used to produce carbon monoxide that will reduce iron from its ore. And also limestone. Limestone is calcium carbonate. And this is used to remove the impurities. So you all have to remember those, students. After I discuss this, I will write it down for you all. So then, all these raw materials are mixed in the correct proportion. Now you can understand this. And powdered finely are charged from the top of the furnace. So all these raw materials, hematite, coke and limestone, they are mixed in the correct ratio and they are powdered finely. You all know the meaning of fine powder, and they are charged from the top of the blast furnace so that they can undergo all the reactions. Now we have looked at this reaction before also, students. There are also, I mentioned to you all that we will be discussing the reduction of iron from hematite, that is Fe2O3, with this process. So if you can remember, the balanced chemical equation, Fe2O3 plus carbon monoxide, this is the compound that is going to reduce iron, and that gives rise to iron plus carbon dioxide. Can you all remember the balanced chemical equation? Because we have O3, there will be 3 CO2 produced. So to get that, we need 3 carbon monoxide, and since there are 2 iron atoms here, we will get 2 iron there. So what is the ratio or the correct proportion? It is 1:3:2:3. So we need to have hematite 1 and 3 carbon monoxide. Accordingly, we need to add coke. And also to remove the impurities from hematite, we need to add calcium carbonate. So that is the correct proportion. So you all can remember this, students. We have discussed it with the uses or why the balanced chemical equation is important to us. So you all know if this is 1 mole, we need 3 moles of carbon monoxide. We will be able to extract 2 moles of iron and 3 moles of carbon dioxide will be evolved. Or accordingly, you know to calculate their masses as well. So I am not going to go into detail there, but you have to remember they are mixed in the correct proportion, they are finely powdered and introduced from the top. And also, as I told you all before, you need to know the reason why we use those three substances. Now, hematite is the iron O from which iron is extracted. Then we have coke. Now, coke, it has two functions actually. Coke is used to produce carbon monoxide. This is carbon monoxide. That reduces iron from its O. So, carbon monoxide is the one that reduces iron, and that is produced from coke. And the other advantage, I told you all before, coke releases lot of energy. So, that is also important. Coke releases high amount of heat energy that helps to increase the temperature of the blast furnace to a range between 1000 degrees Celsius to 1900 degrees Celsius. Because the hot air that is blown in from the bottom, it has a temperature about 650 degrees Celsius. But the temperature inside the blast furnace is between 1000 and 1900 degrees Celsius. And that is achieved when coke burns in air. It releases lot of heat energy. So, that helps to increase the temperature of the furnace. So, you all have to remember that, coke. And then we have limestone. Limestone, that is calcium carbonate, is used to remove the impurities present in hematite in the form of slag. Now, when I discuss the process in detail, students, all the reactions, I will explain to you all what the impurities are. There are actually two impurities, the oxide of silicon and oxide of aluminium. They are known as silica and alumina, and they are combined with calcium oxide produced from calcium carbonate and is removed in the form of slag. So, these are all the reactions that are taking place, and there are some more reactions which I will discuss after this. First, I will explain the blast furnace to you all, the structure of the blast furnace, and thereafter we will discuss all the reactions taking place. So, if we just quickly go through what we have discussed so far, you all have to remember, students. Now, the iron ore is hematite. It has the chemical formula Fe2O3, and the structure used is blast furnace, and the raw materials are fed from the top and the hot air is blown from the bottom, and also there is high amount of temperature 1000 to 1900 degrees Celsius that causes the extraction of iron. Many reactions taking place there, and iron is extracted in the form of molten iron or liquid iron. And also you all need to remember all the 3 raw materials, hematite, coke and limestone, and also why they are introduced or why they are used as raw materials in the blast furnace. So that is the introduction. You all have to remember all these information, students. In addition to that, as I told you all, I will explain the structure of the blast furnace, and thereafter we will discuss all the reactions that take place during the extraction of iron. So here you can see this is the blast furnace. Now this is the structure about 60 meter in height. You can remember 60 meter in height, and that is the blast furnace. Blast furnace. So in this blast furnace structure, you can see this is the raw materials mixed together in their correct proportion, and they are finely ground into powder, ground into fine powder, and they are all fed into the blast furnace from the top. So this contains hematite, plus lime or limestone plus coke. Mixture of, this is the mixture, finely powdered mixture. Those are the raw materials fed from the top. Then on the side you can see we have all the brick walls. This is a brick wall. At the same time, here you can see there are 2 openings. Now, before that, if we look at how raw materials are fed in, here you can see a lever-like structure, students. So, the raw materials, the powder is put into this. When this particular lever is pushed down, through the sides, the raw materials enter into the blast furnace. Then, near that side, you can see there are 2 outlets. So, it's actually a cylindrical kind of structure, not the cylinder shape, but it's complete structure. So, there is an opening at the top through which the air, all the waste gases come out. So, from this side and this side, waste gases come out. For example, if you take carbon dioxide that is produced, that will be given out through that opening. So, that is the upper part of the blast furnace. Then here you can see the temperature range, as I told you, it's going to be 1000 degrees, closer to 1000 degrees at the top, and bottom it will be 1900 degrees Celsius. So from bottom to top, at the bottom only the temperature will be very high. Towards the top the temperature is somewhat less. This is the temperature range. So different reactions take place, and here you can see there are 2 arrows shown. That is where the hot air is blown in. So here hot air is blown in. So this side also we have hot air that is blown in through these openings. Then you can see here, students, this part. Now this dark orange color or reddish color, that substance or what is shown in reddish color is the molten iron. Molten iron or liquid iron. So here we can also say liquid iron. Then here, this part, what you see as black color is called the slag. Now I told you all limestone, it helps to remove the impurities from hematite, and that is removed in the form of slag. So then you can see molten iron is below, slag is above it. Then through this opening we take the liquid iron out. So here liquid iron out. And the top opening is for the slag out. So that is the structure. Blast furnace, 60 meters in height, temperature range between 1000 to 1900, but at the bottom it's more higher, around 1900. Towards the top it's less, about 1000 degrees Celsius. It is made up of the brick wall. So you can see how the powdered mixture of raw materials are fed into the furnace and the waste gases are taken out. Here hot air is blown in from the bottom. And also you can see the molten iron, the slag. Molten iron is taken out from an opening at the bottom, whereas the slag is taken out from an opening which is above that. You all have to remember that. I will explain all the reactions that are taking place. So here, if we consider the reactions taking place, initially we have carbon coke that reacts with oxygen in hot air, forming carbon dioxide first. Then what happens is this carbon dioxide reacts with carbon again, forming carbon monoxide. If you take this reaction, carbon plus oxygen, carbon dioxide, it's balanced. You need to write all balanced chemical equations. Then carbon dioxide plus carbon giving rise to carbon monoxide, but there will be two carbon monoxide formed. That is the balanced reaction. Then this carbon monoxide reacts with the iron ore hematite Fe2O3 with carbon monoxide giving rise to Fe and carbon dioxide. We have already balanced this reaction 3, 2 and 3. You can remember that. So, 1 hematite with 3 carbon monoxide gives rise to 2 iron as well as 3 CO2. Then what happens is we use 3 raw materials. This is one, this is the second one. Then we have calcium carbonate. Calcium carbonate also decomposes to give calcium oxide plus carbon dioxide. That is again another reaction. Then there are 2 impurities present with hematite. One is silica, that is SiO2, and the other one is aluminum, that is Al2O3. These are impurities found in hematite. Now these 2 impurities react with this calcium oxide. So here you can see, students, calcium oxide plus silica gives rise to calcium silicate. This is calcium silicate. So calcium oxide plus silica, this is known as calcium silicate. Then we have calcium oxide with Al2O3 that gives rise to CaAl2O4. That is calcium aluminate. Both these together is what we call as slag. So just look at all the reactions. I will be going through these reactions again also with the explanation. Here carbon reacts with oxygen forming carbon dioxide. Carbon dioxide again reacts with carbon giving rise to carbon monoxide. So this is the compound that is used to reduce iron from O. So that's very important. You have to remember that. Then we have the iron O, Fe2O3 hematite reacting with carbon monoxide, giving iron and releasing carbon dioxide. So this carbon dioxide is one of the waste gases that will go up through the outlet at the top, or else it can even react again with carbon dioxide plus carbon. It can be used up also. Part of it will be used up, part of it will be evolved out. Then again, what happens is calcium carbonate. Here you can see the reaction. Calcium carbonate decomposes to form calcium oxide and carbon dioxide. Then there is silica, SiO2, alumina, Al2O3. These are impurities found in hematite. So what happens is these two impurities react with calcium oxide. Calcium oxide plus silica gives you calcium silicate, and calcium oxide with alumina gives you calcium aluminate. Both of them together is known as slag. And there is an advantage of having slag. Now, if you remember the structure, students. Now here we had it like this. And in this we have the molten iron here. This is the slag. And the rest of the reactants or we can just say reactants, the reactant mixture, everything is there above it. So what happens is we have the molten iron. It's also at high temperature. It's very reactive. Here all the substances are again at high temperature. But this slag acts as a separating layer between the molten iron and the rest of the substances. So within the reactants there are impurities as well. So the slag prevents the reaction of molten iron with the reactants, the substances that are present inside the blast furnace. So that is an advantage of having slag. You have to remember that. So slag prevents the reaction of liquid iron with impurities inside the furnace. So why does the molten iron go down and slag remain at the top? That is again due to density. Molten iron is more denser than slag. So that is another thing you have to remember. Molten iron is more denser than slag. That is why slag is above, molten iron is down. So then when we are drawing them out, now molten iron is drawn out from here, Fe, and the slag is taken out from there. Slag out and molten iron out. So or it can be on the other side as well. That does not matter, but you have to remember, students, always molten iron is taken out from the bottom opening, whereas the slag is taken out from the top opening. The side does not matter, because if you turn the blast furnace around, if you turn the picture the other way, the sides might change. But the position, molten iron from the bottom, slag from the top. So these are all the changes that are taking place inside the blast furnace. You have to remember all the reactions and why all these are necessary for us. And you have to remember this is the advantage of having slag. The slag being there, it actually helps to extract the molten iron in the pure form. So I am sure, students, you all can understand all this. With this, I will move on to the next slide, where again I'll be discussing all these reactions. The reason I am repeating it again is that you can understand it well and also you will remember them well. So I will move on to the next slide. So then again the reaction, students. during extraction of iron, following reactions occur in the blast furnace. So here, these are the reactions taking place inside the blast furnace. The first one, coke burns in air forming carbon dioxide. You know what coke is? Coke is carbon. So carbon plus oxygen in air gives rise to carbon dioxide. That is the first reaction that you need to remember. Coke burns in air forming carbon dioxide. So carbon plus O2, CO2. Then carbon dioxide gas reacts with coke, giving carbon monoxide. So here carbon monoxide is very, very important because that is the compound that reacts with hematite. So carbon dioxide reacts with carbon, that is coke, to give rise to carbon monoxide. And when you balance CO2 plus C, reactants giving rise to 2CO, carbon monoxide. Then the next reaction, carbon monoxide reduces. Now I have explained this term. That particular reaction is known as reducing reaction or reduction of iron from hematite. So that is why we call carbon monoxide as the reducing agent. Reducing agent or compound used to reduce iron from hematite. So that particular reaction is referred to as a reducing reaction. So carbon monoxide reduces the iron ore. This produces liquid iron. What is that reaction? Fe2O3, hematite is the iron ore and the reducing agent is carbon monoxide. We need 3 of those and we get 2 iron as the product, molten iron or liquid iron plus carbon dioxide gas, that is also 3 carbon dioxide gas. So this is the reaction. Fe2O3 plus 3CO giving rise to 2Fe plus 3CO2. And then we have this where calcium carbonate decomposes giving calcium oxide and carbon dioxide. So there we have calcium carbonate decomposing to give calcium oxide and carbon dioxide. So for all these also we need to have high temperature. You all can remember the temperature range is between 1000 degrees Celsius and 1900 degrees Celsius. Then you all know the use of calcium oxide. So this is limestone or lime we can say. Then calcium oxide is actually known as quicklime. Calcium oxide. So this calcium oxide actually helps to remove the impurities, remove silica or oxide of silicon plus alumina, aluminium oxide from the hematite, that is the iron ore. So I'll show you all those 2 reactions in the next slide. These are the reactions you have to remember, students. Starting with carbon reacting with oxygen forming carbon dioxide, then carbon dioxide reacts with carbon giving carbon monoxide. Then we have Fe2O3 plus carbon monoxide giving Fe and carbon dioxide. Then the decomposition of calcium carbonate to give rise to calcium oxide or what we call as quicklime and carbon dioxide. So with that, we will move on to the next slide. So silicon dioxide or silica, silicon dioxide or silica, aluminium oxide or alumina. I gave you all the chemical formula present as impurities in the iron ore. React with calcium oxide formed by the decomposition of limestone giving the slag. A mixture of calcium silicate, so you have to remember all these, calcium silicate and calcium aluminate. So I have introduced those reactions to you all. Silicon dioxide or silica, that is SiO2. Then we have aluminium oxide, Al2O3, that is also known as alumina. So those are the two reactions that take place here. So what happens? There you can see they give a mixture of calcium silicate and calcium aluminate. So there you can see the slag actually floats on molten iron, and molten iron and liquid slag are separately flown out. So here if we write down the reactions, again if I show you all. So here if I write the reaction, you all know from calcium carbonate, when it decomposes, calcium oxide is formed. This actually reacts with both silica and alumina. Silicon dioxide and aluminium oxide. I will write the reactions here. So, calcium oxide plus SiO2 gives rise to calcium silicate, CaSiO3. This is, you can remember easily students, this is also a chemical combination reaction. Calcium oxide combines with silica forming calcium silicate, and calcium oxide with alumina or aluminium oxide, Al2O3, gives rise to calcium aluminate, CaAl2O4. They all get combined. Both the compounds get combined together. So both these together is what we call as slag. So these two together are known as slag. So calcium silicate and calcium aluminate. You have to remember the chemical formulae, students. And I have already explained the advantage of having slag. Slag prevents the reaction of molten iron or liquid iron with the impurities present inside the blast furnace. That is an advantage. So I will write that here as well. Slag prevents the reaction of liquid iron with the impurities present in the blast furnace So that is an advantage of having slag. I am sure with that you all are very clear with all the reactions taking place inside the blast furnace. You have to remember all the balanced chemical equations. Again, to summarize, the three raw materials, hematite, Fe2O3, limestone calcium carbonate, and coke, that is carbon. They are all fed from the top. Hot air is blown from the bottom. Then all the reactions. Carbon monoxide is the compound that reduces iron from hematite. So we get iron in the form of liquid iron, and that is drawn out from the bottom opening in the blast furnace. Above that there is slag. Slag is the mixture of calcium silicate and calcium aluminate. Because silica and alumina or silicon dioxide and aluminium oxide are present as impurities in hematite, that is the iron ore. So they react with calcium oxide forming the slag. So slag anyway prevents the reaction of iron, molten iron or liquid iron with the impurities again. So that is the summary of the extraction of iron. I am sure you all can understand that. With that, students, I will move on to the next slide. So then we have an assignment. The first part of the assignment is to collect information about the iron industry in ancient Sri Lanka. So earlier also with extra knowledge students, we discussed that near the Samanala River, when archaeologists did an excavation, they were able to find the evidences for the presence of a furnace that was operated using the wind energy, windmill. So from there, they were able to rebuild that furnace and extract iron. Smelting of iron, you can remember that. So that is one information that you already know. Similar to this, you can refer the magazines, papers, there are so many journals or even the internet, and you can gather more information about this iron industry in ancient Sri Lanka. And also you all know, for the Emperor of Arab, the sword was made from our country, Serendip. So that is what you need to do first. Then the second one, iron is used to make alloys. You know the meaning of alloys. When one metal is mixed with other metals or even a non-metal to produce a substance that can be used in day-to-day life, we call that mixture as an alloy. For example, you all are familiar with brass. Brass is an alloy of copper and zinc. Like that, there are many alloys used from iron. That also you are familiar with. Steel, stainless steel, different types of steel that are used are all alloys of iron. So, iron is used to make alloys. Prepare a table comprising the alloys of iron, the new properties imparted of them, and the uses of items made of those alloys because of those properties. So, they want you to make a table with many different alloys. For example, I will give you all two alloys. Now, you can remember I said alloy steel. This is for the second question. Steel is an alloy of iron. In steel, there is iron, Fe, and carbon, C. So, steel is an alloy containing iron and carbon. Usually, it is less rusting. Normally, iron rusts faster. But compared to that, steel rusts a little slowly, and also steel has the ability to withstand more tension and it can bear more pressure. So, because of that, steel is more stronger, we can say, than iron. And it can be used to make many structures. So, structures made up of steel, you can get a lot of examples. So, this is more stronger and harder than iron. And we can use this steel to make many structures. You can refer those as well. So, here I told you all, I'll just give you all an introduction to the different types of alloys. Then we have stainless steel. Now, stainless steel is what we use in households. Spoon, fork, knife, then even the plates, we have some dishes, cutlery, culinary, all these made up of stainless steel. Why do we call it stainless steel? It does not rust very easily. Now, this is again an alloy. So, here there is iron, Fe, then there is nickel, Ni, chromium, Cr. That is how we get stainless steel. Stainless steel is an alloy of iron with nickel and chromium. So, from the name itself, you know stainless steel does not rust easily. So, does not rust easily. We can use these to make many objects that should not rust quickly. So, all the household appliances, lot of household appliances, as well as even surgical instruments, what we use in the lab, most of those can be made from stainless steel. So, as examples, here of course, I'm not going to include the examples. You can write a lot. And in this, the steel, stainless steel, there are other different grades of steel. For example, I told you all surgical instrument. So there we use surgical grade steel. So there, in addition to iron, there can be other metals or even carbon, different compositions, so that the grade is even more better. It is a better quality steel that never rust. Because you all know when you are performing a surgery, you can't use a surgical instrument, a surgical needle that has rusted. You can't afford that. So that can lead to a lot of complications. So to prevent that, they use the surgical grade steel. Like that, there are different grades of steel. So I have introduced only just 2 types of steel. Those are alloys of iron. So the normal steel has iron and carbon in it. And stainless steel has iron, then nickel and chromium in it. And there are many other types of steel. Then here, discuss with the teacher the advantage, if any, of the existence of the slag in the blast furnace. This, of course, I have explained to you all so many times before also with the extraction process. So there they have asked advantage, if any, of the existence of slag in the blast furnace, because slag is actually the byproduct or the waste product, because impurities are aluminium oxide and silicon dioxide. So they are removed in the form of slag. So that is actually the removal of waste materials. But there it becomes an advantage when it exists in the blast furnace. So again, since this has been asked as a question, I will write that as well. Third one, slag is present above liquid iron in the blast furnace. Because it is less denser than iron. So that is why it is present above liquid iron. But what is the advantage? Advantage is it, or we can say slag prevents the reaction of liquid iron with the impurities present in the blast furnace. So because it is above liquid iron inside the blast furnace, it prevents the reaction of liquid iron with other impurities or other compounds that are other substances present inside the blast furnace. So because of that, we are able to take out the liquid iron in the pure form. So that is an advantage. So here students, all these, there are 3 parts to the assignment. One is to collect information regarding iron industry in ancient Sri Lanka. That I told you all we had some information. In addition to that, you can refer up some more information. Then alloys also, I introduced only 2 alloys to you all, but as I said, there are so many other types of alloy. Even marine grade steel, then there is the surgical grade steel, like that. There are different types of steel and different alloys of iron. So 2 steel and stainless steel. Then the advantage of existence of the slag in the blast furnace, that also Already I have told you all, but again here I have given the explanation. So with that students, I am sure you all have a very good understanding about the extraction process of iron. And also you all know many uses of iron. So with that, I have completed the extraction of iron. This is a metal that has moderate reactivity. So they are extracted using an element or a compound. So you can remember hematite is the iron ore. We used carbon monoxide, a compound that is the compound that reduces iron from hematite. So you have to remember that. Then we have the metals at the lower part of the activity series, or the last few metals in the activity series: silver, platinum and gold. Those are usually native metals. They don't react very easily. So these metals are extracted using physical separation techniques because they exist as metals, but they do have some impurities in their ore. So that is what I am going to discuss in the next slide. So extraction of gold. So gold, Au, is a metal that has longer historical relationships with humans than even iron does. Historically, there is lot of relationship of gold with humans. Even now, we use gold mostly as jewelry because it does not react with any other substances. The color, the shine is not lost. It does not tarnish. So, because of that, it is very valuable and it is very attractive as well. That is why there is lot of relationship. There are evidences for the utilization of gold to make coins, various statues and documents. So, coins, various statues as well as documents. So, now let us see how this metal is extracted. Gold, which is placed at the bottom of the activity series. So, it is at the bottom of the activity series, does not react with any active component of the atmosphere under normal conditions. Very, very important. Does not react with any component of the atmosphere under normal conditions. So, in our day-to-day life, if we use gold, they do not react with any component of the atmosphere. So, because of that, they do not tarnish and they remain shiny, they remain as the metal. No change to the properties. Therefore, it occurs as the native metal in nature. But it is mixed with other impurities. That is important. So, although it exists as the native metal, there are some impurities present with this metal. So, a certain amount of impurities can be removed by sifting. This is the process. A physical separation method or a mechanical separation method. Sifting the ore containing gold. So, a certain amount of impurities can be removed by sifting the ore containing gold. So, when we say sifting, this is how it is done. The density of gold is very high. So, it has very high density. Therefore, when the ore is powdered finely and mixed into a drain of water, gold settles down first on the bottom. The metal separated by such physical methods is purified further by various methods. So, here they are separated from the impurity by a physical method. Then again, they can even be purified further using other methods. We can use chemical methods that I will discuss in the next slide. So, this is how sifting is done. Now, if there is flowing water and if there is a slight inclination, what they do is they have a ladder-like structure that is used for this sifting process. So, in that there are plates like that. It is kept at an inclination, and here what they do is they put the gold ore powder. So, this is the finely powdered gold O. So here what happens is through these water flows. So there is water flow in this direction. So with water the gold O is also flowing, but because it is highly dense, the gold settles here. Gold settles down because of its high density. But the impurities, they just keep on flowing. Impurities flow with water. This is what we call as sifting of the gold ore. So what we do is we finely powder the gold ore and we allow it to flow with a drain of water, and because of the high density, if it is just a small stream, with that the gold can flow. So it settles down in this particular structure because of its high density, and the impurities actually just flow away with water. So that is the method of sifting ore. It is a physical separation method. So here some of the impurities are removed, but if there are other impurities, then they can be separated using chemical methods as well. So that is actually discussed as an extra knowledge for you all. So this is a simple technique. You need to remember gold is a native metal. So it exists as a metal in nature. Only the impurities need to be removed. For that we use physical methods. Example, sifting. And that is done because gold has high density. That is possible because of the high density of gold. So with that students, I will move on to the next slide. So here, as I told you all, for extra knowledge, presently solvents that dissolve gold have been discovered. When the metal with impurities is dissolved in these solvents, only gold dissolves. In order to get the metal that has gone into the solution, it is displaced by another metal. So what do? We have the gold O, and we add a solvent. So it dissolves. So here in this what happens is gold dissolves in the solvent. Now for this there are different solvents, students. One of the common solvents that can be used to dissolve gold is known as aqua regia, or what we call as royal water. That is a mixture of two acids, concentrated nitric acid and concentrated hydrochloric acid, in the ratio of 1:3. That is one solvent that can be used to dissolve gold. Then there are other solvents which have been recently found, cyanide of sodium or potassium. They also can dissolve gold. So then you have the gold dissolved in the solvent. Thereafter what happens is we displace it using another metal. Displace gold by another metal. Now you all are familiar with this displacement reaction. From a salt solution of a particular metal, a metal that is more reactive will displace it. You can remember zinc displaces copper. So gold is the last metal in the activity series. So any metal that is above it can be used to displace gold. So that is how the gold is separated from the other impurities. So as an example, as I told you all before, royal water, or what you call as aqua regia. So aqua means water, regia is royal. Royal water is a mixture of acids that can be used to dissolve gold. So like this, you can also refer into different solutions or solvents that can dissolve gold. So with that, students, I have come to the end of this chapter. In this chapter, we discuss the process of extraction of iron from hematite using the blast furnace. That was discussed in detail. So as I told you all, you have to remember all the reactions. Then we looked at how gold is separated from its ore. So because it's a native metal, you don't have to have strong separation techniques. A physical method is more than enough. The sifting process and the rest of the impurities can be removed by dissolving gold in a solvent and then displacing it by another metal. So I'm sure you all have a good understanding of this topic. In the next chapter, students, I will be discussing the preparation of gases in the laboratory, their properties and their uses.